the next big thing going on is exam 1. And that's this Friday. And the topics are everything up through strain and constitutive relationship. So you're definitely going to want to have your calculator working with the compliance matrix and rotation matrix. So yeah. Make sure your calculator can do compliance and rotation matrix calculations. All right, anybody have any questions about the test? Anybody have any homework questions you want me to go over?
Weekly assignment, number 1. What does a stress cube look like for a tensile test? Is it just like a uniaxial stress cube?
Yes.
Okay.
That's right.
Okay, we were just, discussing that.
Yep, exactly. Any other questions? Okay, so we're talking about principal stresses now. I talked sort of about I told you how we're going to calculate it in practice, and it's just going to be, it's the easiest, quickest calculation. One other thing that I want to tell you, so if you ever, you have a principal stress tensor, so let's call that, that looks like sigma 1, sigma 2, sigma 3 down the main diagonal. So that would be a principal stress tensor. And let's say sigma 2 is the middle eigenvalue. Okay. Then the maximum shear stress is, well, let's call this sigma 1 is the maximum, sigma 3 is the minimum. Bless you. Okay. So the maximum shear stress is going to be the max minus the min divided by 2. And usually that's all you want is just the value of that shear stress. But if you ever want a stress tensor, if you ever want the full stress tensor that contains the maximum shear stress, and what this would be is a stress tensor actually containing the maximum absolute value of shear stress. This is really the maximum shear stress because it always comes out positive. Then all you do is rotate the coordinate system, 45 degrees, about the middle principal stress axis. So in the case above, what axis is associated with the middle principal stress?
Y.
Y. And so we'd go, Q would be cosine of 45, 0, negative sine of 45, 0, 1, 0, sine of 45, 0, cosine of 45. And then you just go Q, sigma principal, let's call it, and then Q transpose. And so if you did this calculation and you got a value here of 1.5 megapascals, okay, then doing this calculation from the principal stress tensor would give you a new stress tensor that somewhere has a shear stress of either 1.5 megapascals or negative 1.5 megapascals. Okay. Having that stress tensor isn't super useful, but just as a way to get used to rotation matrices and interpreting these different coordinate systems, I'll make you do that a few times. But really for the purposes of figuring out if something's going to fail or whatever, all you really need is that value. Yes?
Why wouldn't it be useful for things like bone or wood?
To find the actual stress tensor?
Yeah.
Yeah. Well, usually, so brittle materials like that are going to tend to fail in shear, and it tends to be the case that failure is going to just be determined by the maximum shear stress alone. But I'm sure there are more complicated ways of calculating whether something is going to break that take all the stress elements into account. There are a bunch of ways to calculate the damage done to a material using stresses and strains combined in different ways. But the simplest one and the most common one you see is just like, so is this piece of wood going to break? Are we going to have fracture in this bone? Just look at the maximum shear stress. Okay, so now we're going to talk about the mathematical meaning of the principal stresses. And I'm going to do this because this will give you sort of an idea of how eigenvalues and eigenvectors work. So for a matrix, I'm going to call it, just give it the values, sigma xx, xy, xz. In our case, this is a stress tensor, so I'm going to use the symmetry. So sigma xy again, yy, yz, then xz again, yz again, and zz. And we're going to be looking for a unit vector and So we're going to find a unit vector n, and a constant lambda that satisfies this equation. So we got our stress tensor again, xx, xy, xz, xy, yy, yz, xz, yz, zz. And what we're looking for is, so we're looking for both of these things, a unit vector and a corresponding value. And we've found these values when you can multiply the matrix by this unit vector. And it's equal to the constant times the unit vector. So that's what we're trying to find. Okay. In our case, you can make really good physical sense out of this. We're looking for cases where the stress tensor in this new coordinate system only has normal elements, right? That's what the principal stresses are. Remember that? And so what we're doing here is, well, what's this calculation doing? Remember, this is how you calculate tractions on a face. You multiply a unit outward facing normal times the stress tensor. So what we're saying here is, if you multiply the stress tensor by the right outward facing normal, okay, you get back traction vectors that are parallel to that outward facing normal. Okay? You see that? And so, in other words, what we're saying is we're going to find outward facing normals where the tractions are perpendicular to the face. There's no shear components on that traction. So it's sort of a simple idea, you know, makes sense. So how are we going to do this calculation? One thing I want to say before we get into that is, so I said this has to be a unit vector. Notice that this really, if you can find a unit vector that works with a value of lambda, it works for any multiple of that unit vector also. Because think about, so say you have this equation that works for a unit vector, and now multiply that unit vector by 54.68, you know? The math lets you pull that 54.68 out here. It lets you pull it out here. So of course they still work, you know? And so we're gonna see that non-uniqueness happen. And that's why we're just always gonna choose, let's make it a unit vector, okay? But there's always infinitely many solutions parallel to each other, okay? Okay, so I'm going to make you write this matrix one more time. One more? Two more, maybe. So another way we can write this is we can write sigma xx, sigma xy, sigma xz, xy, yy, yz, xz, yz, zz, times this vector is equal to lambda 0, 0, 0 lambda 0, 0, 0 lambda times nx, ny, nz. So first you could just multiply that out and you'd see that you get this. What you get out of this is lambda times nx for the x component, lambda times ny for the y component, lambda times nz for the z component. You could also think of this as taking that lambda and multiplying it by what's called the identity matrix, which is just ones in the diagonal. So anyways, these are two different ways of writing the exact same thing. But now that we have it like this, we can do the algebra and subtract the right side from both sides. Okay, so if I subtract from both sides, we get the component, the element sigma xx minus lambda there. Then sigma xy, sigma xz, sigma xy. Now for the next component, again, we have sigma yy minus lambda, sigma yz, sigma xz, sigma yz, and then this component is sigma zz minus lambda. And then we're multiplying this by nx, ny, and z. And we're saying, so now we've done this by subtracting what's on the right side from both sides. So now this is just zeros. You see how that worked? Because you can just subtract element by element. And when would this not have a solution? Well, notice that, or I guess really, like when would you get a trivial solution out of this? This solution would be useless to us if this matrix had an inverse, okay? So if this matrix has an inverse, you could multiply its inverse to this side, and you just end up with nx, ny, and z. Multiply the inverse times this side, and you get zeros, and your solution would be that nx, ny, and z is equal to zeros.
So would that happen like if there were no stresses?
No, it just doesn't mean anything. And so what we're going to do is we're going to require that this isn't invertible. Okay, so solutions occur when the matrix on the left is non-invertible. Okay, so what does it take for a matrix to not be invertible? There's a pretty simple test for whether a matrix is invertible, and that is when the determinant is equal to 0. Okay, so it's non-invertible when the determinant is equal to 0. So now we've turned this problem into, we have this matrix over here on the left, and we just want to find when the determinant is equal to 0. How many of you guys have done determinants before? Yeah, seen it before. Well, it's easy to do. So the determinant looks something like this in this case. So you have the quantity sigma xx minus lambda times the quantity sigma yy minus lambda times sigma z minus lambda. You're never going to have to do this in this class. And then minus sigma yz squared. That's the first part of it. What I'm doing here, by the way, is I'm taking this first element here, and I'm taking that and then multiplying it by sort of like a cross product kind of thing. This times this minus this times this. Okay. Now I'm going to go, because y always has to be the difficult one, now we're going to go minus this thing times the determinant that you get from crossing out this row and this row. So this times this minus this times this. So now we go minus sigma xy times the quantity sigma xy times the quantity sigma z minus lambda minus sigma xz sigma, that's sigma xz squared. And then we're going to do it with the last one in this row, so plus sigma xz times the quantity sigma xy sigma yz. Is that right? Yes. Minus sigma xz times the quantity sigma yy minus lambda. And all this is equal to 0. Okay, well, look at this and tell me, so this is just solving a blank degree polynomial. What's the degree of that polynomial?
2.
Wrong. Three, it's just 3. So the stuff in the parentheses, in the brackets is 2, and then you're multiplying by 1 more on the outside. So third degree. Okay, so that's all you're doing. And if I wanted to make a, so if I was trying to put a problem on a test where you had to calculate eigenvalues and or eigenvectors, and I knew not everybody had a calculator that did eigenvalues or eigenvectors, the easy way for me to do that would be to make one of the roots of this polynomial be 0, okay? And then this thing would reduce to a quadratic, and then it's easy, anybody can solve a quadratic, you know. So, by the way, if one root is 0, then it's just solving a quadratic equation. So solving that gives you the three roots of the, and I mean, it makes sense, I guess, that it has to be a third degree polynomial because we know we're looking for three roots, the three normal stresses. Okay. So the three roots are the three normal stresses of the principal stress tensor. And so then once you found those three roots, just one by one, you plug those roots into this equation and solve for this unit vector. Okay. Each root has a corresponding eigenvector that you get for solving, nx and y and z. And that is parallel to the corresponding axis of the principal coordinate system. So for our purposes, we pretty much just want those principal stress values. So solving for the eigenvalues is enough. But if you wanted to know what the coordinate system was that corresponded to your new principal stress tensor, you'd figure it out by finding these eigenvectors, which basically are each one of those is the outward facing normal of your face, So let's do one example like that just by hand. In the meantime, I'm just going to have you do problems using your calculators, and I'm never going to give you an assignment where you have to do stuff like this. But let's just, do I have an example here? I hope so. Okay, so this is a pre-example. Okay, so if I wanted to do, so as somebody trying to come up with a test question or whatever, and I want to be able to do a principal stress question that you can do by hand, how would I go about doing that? How would I go about coming up with a stress tensor that has a nicely behaved principal stress tensor with one of the elements being 0,
Biaxial?
Yeah, so that's what I want. But the question is a bad way to do it would be to just start filling out values of a stress tensor, and just hope you hit it, But that's very unlikely to work. But what I'm going to do instead, so here's my pre-example question. So I want to find a stress tensor with 1, 0 principal stress. So the way I'm going to do it is I'm going to first just define my, I'm first going to define what I want as my principal stress tensor. Okay. So I'm going to say, first, I'll decide I want my principal stress tensor to be, let's make something nice. And so let's say we want it to be 10, 0, 0, 0, negative 5, 0, 0, 0, 0. Okay. And then just give the coordinate system a spin, So I'm going to take this, and now I'm just going to rotate the coordinate system to mix up the values, So what do we want to, let's go, so now we're going to rotate the CS, let's say 30 degrees about the y-axis. And then let's do 20 degrees about the z-axis. Okay, those are totally arbitrary, but it's so that you don't recognize this stress tensor, and then we have to do the calculation. The rotation about the y-axis, I have 7.5, 0, 4.33, 0, negative 5, 0, 4.33, 0, 2.5. Did anyone else do this? Mm-hmm. Did you get that same stuff? Mm-hmm. That's a good sign. Okay, and now, so already we have something where the eigenvalues aren't easily, recognizable, and I'm going to do. So after the z coordinate system rotation, now I get 6.038, negative 4.017, 4.069, negative 4.017, negative 3.538, negative 1.481, 4.069, negative 1.481, 2.5. And there's no way to look at that and spot what the eigenvalues are, but because of the way we did it, we happen to know that the eigenvalues of this are 10, negative 5, and 0. Okay. Okay, so how are we going to calculate this? So this is the example now. We want to find the principal stresses with an eigenvector for each one. Just using the definition of principal stress. Okay, so yeah, if you just saw this on a homework problem or an exam or something, you were given this matrix and you were asked to find a maximum or a minimum normal stress or a maximum shear stress or whatever, the way you would do this is super quick and simple. You just use the eigenvalue command either on your calculator or you'd go to Wolfram Alpha to do it. So not on an exam, I bet we've been talking about that, but like on homework, you'd go to whatever eigenvalue solver, you'd plug it in, you'd plug in the eigenvector solver, and it would just do it for you instantly. But so what we're going to do is we are going to go back to this idea where we're going to calculate the determinant of this matrix and set it equal to 0. And then we're going to have a quadratic equation to solve to get the two non-zero values of sigma, or of lambda in this case. Okay. Okay, so we want to take the determinant of 6.038 minus lambda, negative 4.017, 4.069, negative 4.017, negative 3.538 minus lambda, negative 1.481, 4.069, negative 1.481, and then 2.5 minus lambda. And we're going to take the determinant. So the symbol for taking the determinant of a matrix is like absolute value of the matrix. And we're going to set it equal to 0. So we have 6.038 minus lambda times the quantity negative 3.538 minus lambda times the quantity 2.5 minus lambda, and then plus 1.481 squared. And then we have minus, but this is negative, so I'll just do this as plus 4.017 times the quantity negative 4.017 times the quantity 2.5 minus lambda minus 4.069 times negative 1.481 and then plus the quantity 2.5 minus lambda. No, sorry, I'm going the wrong way. Plus 4.069 times the quantity negative 4.017 times negative 1.481 minus 4.069 times the quantity negative 3.538 minus lambda. And we're going to set all this equal to 0. And this is a super pain. Well, what time is it? It's time to stop. So I'll get this into the form of a third degree polynomial, and then we'll see that it's just a quadratic, and then we'll use the quadratic formula to solve, and then we'll go back and calculate at least one of the eigenvectors to see, so you can see how that works. But one thing you see here is in the old days of having to do stuff by hand, you can imagine why they got away from doing it this way. They found a clever way called Moore's circle to do similar calculations without having to go through all this stuff. By hand, it's a nightmare, you know. But when you have computers and calculators that can do these calculations for you, this is a just much quicker, simpler, more intuitive way to do it. Okay, any questions right now? So we'll finish this next time. And remember, if you have any questions related to the test, feel free to bring them on Wednesday and we can talk about them. Did you have a question?